Welcome back. So today we're going to pick up where we left off last time while trying to develop this mathematical model for the physics that we learned from our Stern-Gerlach experiment. And we're gonna also make this system go beyond what we understand from 245. We're really going to quantumize the system. Okay, we're gonna apply some of our ideas for what the quantum world means. In other words, we're going to develop postulates that help us to build this mathematical system and really understand why quantum mechanics, and that is, why are quantum systems different from some of the classical systems that we have, even though many of the mathematical structures look the same. Okay, so to remind us, we're going to start with this idea of a state that we developed in the last lecture. Okay, so on the left-hand side, I have this vector, right, which we're going to call psi. And on the right-hand side, I've explicitly decomposed psi onto the spin up and spin down states, right, onto plus and minus. Now, there's a lot of sociology that went into writing down this expression, right? First, I had to have an experiment, right, that was able to measure the z component of the magnetic dipole moment. I had to do that and find out that there are only two possible outcomes, and those two possible outcomes had two measurements associated with them, right? So writing something down quickly like this hides a lot of the physics that went into the system, right? That we're developing a mathematical model to describe a very specific system. And the fact that there are two states, that there are two basis vectors, is really a statement about the experiment that I was doing and the measurements that I was taking, right? We also wrote down last time some more general formulas that we could perhaps use if that system were larger. But this is explicitly for the Stern-Gerlach experiment that we've been building in the last couple of days. And so I want to think about now what we're going to call the postulate of measurement. And that is, if I have this general state, which we don't know, right? It's some vector in this abstract space. And that vector, that electron, right, which belongs in this space, gets shot through my Stern-Gerlach experiment. And I want to think about, well, what happens, right? Well, we measure, right, by looking at the little light popping up on the screen, or putting a little filter only to allow the ones that got deflected upward to pass through. We have taken a measurement of that state, and therefore we know on the right-hand side, say, right, I'm making a choice, right? I'm going to say, we've identified that this state, the outcome of this experiment, that the measurement that I took is a positive component of the spin, and therefore I've done something, right? I've actually taken a measurement. Now, I should write one possibility here, right? Because it's also possible that I would have gotten the down one, right? But I'm not saying that. I'm saying that the thing that I got out of this measurement is I've identified the output is positive. And so what we're saying is that the thing that I measured when I said this electron has a z component of its angular momentum, a z component of its spin that's up. When I made that measurement, what I'm saying is that the state is a pure basis vector, right? It exactly, in the process of measurement, is one of the basis vectors. Right? It is not, well, I shouldn't say it that way, but I don't want to think about it, right, as being some general state with some unknown set of expansion coefficients, because it's not anymore. I measured it to have spin up, and therefore that state is the plus state. It is the basis vector. And so what happens when we measure something, and this is the postulate, when we make a measurement of a system, or when we make a measurement of a state, that state collapses into one of the basis vectors. It collapses into one of the pure states, because those pure states have a single measurement associated with them. And that's why in quantum mechanics we can't measure, we only have the up and the down measurements, right? We don't have a middle ground, right? In quantum mechanics, I can't talk about having a zero component of the angular momentum for this particular for this particular state, because it can't have that outcome. And therefore, the collapse is that when I make a measurement of a state, I'm in a pure state. I'm in an eigenvector. I have measured an eigenvalue, and therefore I have an eigenvector. And as a quick aside, to me, this is I think about this in a way that's different than I think about classical physics. So if I go back to that idea of where have I seen this language before, and I have a vibrating atom, right, that's made up of a bunch of vibrational modes, and I take and I study that system, it's possible that I can figure out how much of that atom is how much of that particular atom is vibrating in all of the different modes, right? And I can calculate all of those expansion coefficients. In the quantum language, the postulate is that I can't do that operation. If I have a single object, if I have a single electron and I take a measurement, that measurement is only one pure state. It's only going to have one outcome. And I'm not going to be able to measure all of the different expansion coefficients. In fact, one could argue that I can't measure any of the expansion coefficients. I only get one of those possible outcomes out. And I'm going to allow us that moment of like mind-blowingness, right? To be like, well, what does that mean? Like, if I have this input state and it comes out and it's only spin up now, does that mean it was always spin up? And it just so happens that, this thing just deflected it upwards and some other state was spin minus and it was the one that went downwards. And what is so? Do the probability amplitudes mean anything, or where was I going with this? And is it a mathematical trick? And what does the thing? These are all great questions, right? And we will address some of them as the semester goes on. But this is also really an active place for research, right? There are people around you who are thinking about what it really means to take a quantum measurement. And therefore, it's okay to be a little confused by this at first and to understand that what we're doing is we're coming up with a mathematical model that describes what happens when we do the experiment. Because when we actually put the screen there, electrons either hit in the up measurement or the down measurement. They don't hit in the middle, right? And therefore, a single particle or a single state or a single vector, when I take a measurement, I am then in a pure eigenstate. I'm in a pure basis vector. I'm only spin up or spin down. And, there are great information, blah, 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 but we'll get to that, okay? But for now, this postulate says that the measurement tells me which of these states I'm in. So the second postulate that we're gonna grapple with then is, well, what do these probability amplitudes mean if I know that when I actually take a measurement, I'm never going to be able to figure out what they were. And what the probability amplitudes mean are somehow the likelihood of taking those measurements. So if I knew the probability amplitudes, maybe I could give some probabilistic estimate, or I could make some guess as to what the likelihood of different measurements were going to be at the end of the day, right? After I took the measurement. And so we postulate that the probability of measuring some state is going to be the act of projecting my state. The probability of measuring some value, some pure state, is the projection of my state onto that basis vector, right? So that's this operation here where I'm trying to get that expansion coefficient. And then I take that expansion coefficient and I square it, and that gives me the probability. And that's why we're careful to use probability amplitude to describe the expansion coefficient, and the probability to be the modulus, or the mod squared, or the complex conjugate times itself of the expansion coefficient. And so let's just do this algebra for the example that I have here. So if I have the state above and I try to calculate the probability of measuring plus, well, I would take the dot product, right, of plus with the state, which is alpha plus beta minus, and here I'm just so happy, right, that I have a beautifully orthonormal basis because the plus dot minus is going to give me 0, plus dot plus is going to give me 1, and I end up with the modulus squared of alpha, which is, of course, defined to be alpha star alpha. Right? And that's the relationship between the expansion coefficients and the probability amplitudes and the probabilities themselves. Okay? And again, as we identify things that people sort of commonly do as mistakes when learning quantum mechanics, oftentimes we forget that it's these probability densities, right? The probability amplitudes have to be squared in order to give us the probabilities. So that leads us to this idea of a sort of properly normalized state. After all, if my expansion coefficients are the probabilities, then the sum of the square of all of the expansion coefficients better add up to 1, right? Because they're probabilities, right? And so that's the idea that the modulus of the state itself has to equal 1. And of course, these all sound like dot product things. These are things that you've done before. So if I have this same state where psi is equal to alpha plus beta minus, and I just explicitly took the complex conjugate of it, right, because I wanted both the ket and the bra version, and I start to write this out, well, I get the bra version is going to be alpha star plus beta star minus with alpha plus beta minus, right? And these are in principle 4 terms, right? But orthonormality tells me that plus dot plus is going to be 1, minus dot minus is going to be 1, and the cross terms are 0. And so this turns out to be alpha star alpha plus beta star beta, which in human terms is just that all of the probabilities have to equal 1 if I'm going to call this a normalized state. Okay? And so the idea of normalization then makes it easier for us to say that the probability amplitudes, right, when I square them, I get the probabilities, and those probabilities have to represent all possible outcomes. Okay? And that also brings a little bit of physics back to it, because these expansion coefficients then have to, they have to obey some rule in order to give us information about what the possible outcome of that state is, or what the possible measurements of that state is. And now I'm talking, and we're going to talk in person, and you're going to read the book, and you're going to read the Wikipedia, and I just wanted to, there's so many words to describe this that I thought it would be important to write some of them down, right? So where you might have said where you might have said basis, right, or decomposition, we also sometimes in quantum call that a representation, right? So if I have a certain set of basis vectors, that's a way to represent states, right? It's a way to explicitly write them down. And so we often call that decomposition a representation. Okay? And what we think about as a basis vector is also commonly called a quantum state, right? Spin up or spin down are my 2 quantum states, right? They represent 2 different basis vectors. We also call those pure states, okay? Because they have a measurement associated with it, right? And in fact, if you measure it once and then you measure it exactly using the same device again, you're going to get the same thing out, right? Because you're in this pure state. And then there's also this idea of having sort of a general vector, right? So what does it mean to be a vector in one of these spaces? Well, that vector, if it's not a pure state, is going to be a superposition state, right? Because I've added different pure states together with different coefficients in front of them, or something that we often call a mixed state, right? Because it's a state that's made up of many different eigenvectors, many different basis vectors, many different quantum states, right? And so these are just some of the words that you'll see as you piece together how this is actually going to work. But let's spend the rest of our time on this video thinking about why is this so cool, okay? And now I want to go back to that idea that we talked about at the end of the last video, where the Stern-Galich experiment in the z direction, right, defines a particular basis for this 2-dimensional system. But if I take that Stern-Galich experiment and I rotate it, right, then I can expect that that basis is not going to be the same, say, if I put the Stern-Galich experiment in the x direction. Okay? I still expect there to be 2 outcomes because it's still a two-dimensional system, right? But instead of projecting it on, or asking the question of what's the measurement of the z component of the magnetic dipole moment, I'm asking myself, what is the x component of the magnetic dipole moment? And I expect that those two things they're different basis vectors. It's a different experiment, right? It's a different way of talking about those electrons that I'm shooting through my Stern-Galich experiment. And so what does this mean with our measurement postulate? Well, okay, so I have 4 different states now. I have my plus and minus from the Z machine, and I have my plus and minus from the X machine. And I'm going to use the textbook's notation here. So the Z ones don't have a subscript, but if I do it in the X or Y direction, those are going to have a subscript. Here they're red and green, although that won't be true in a slide or two, but just to show us the difference between the two. Right? I now have 4 different basis vectors, but I know that the system is only 2-dimensional, and therefore the plus x state must be made of the plus and minus states, right? And the plus state must be made of the plus x and minus x states. And I'm just going to give those to you for now, right? We'll do an exercise where we try to derive what these look like, but basically, I can write down, well, what does the plus state look like in terms of the plus x and minus x states? And what does the minus x state look like in terms of the plus and minus states? And I find that they're all linear combinations of each other, right? That if I have a particle that has a plus that's spin up, right? That has a positive component of its magnetic dipole moment in the z direction, then it's going to be a mixed state with respect to the basis vectors of the Stern-Galich experiment in the x direction, right? And so what this is saying is that if I measure the z component, then that measurement of the z component tells me that I'm no longer in a pure state, or maybe I never was, but I'm not in a pure state for the machine that's oriented sideways. And therefore, if I send that plus into the machine that's oriented sideways, I can make a prediction as to whether that plus is going to be a plus x or a minus x, right? I have the probability amplitudes. They're right here, right? And in fact, if I square 1 over the square root of 2, I find out that there's equal probability of being plus x or minus x, right? But I don't know which one it's going to end up being. And that's where things really kind of get cool, right? Because by collapsing into the plus state, I now have no information about what the x component of the magnetic dipole moment is, right? Because I measured it to be in the plus state. And all of this magic, all of this sort of quantum coolness, right, really comes down to the linear algebra that we know and the observation that this system is finite dimensional, right? And that there are only 2 possible measurements. So what we often like to do is picture like, a state walks into, I have a general state psi, right? This blue friend on the far left. Blue friend walks through the Stern-Galich experiment in the z direction, and I then take a measurement, right? And I can say what is the z component of its angular momentum. I can set up a little gate, right? I can make a hole in the screen somewhere so that only the spin up particles get through. But if I'm in that spin up particle state, right, then I know that I have a 50% chance of being a plus x state and a 50% chance of being a minus x state, right? And so if that spin up state goes into this second Stern-Galich experiment, I don't know what's going to come out, right? Until I actually make the measurement, right? And it's likely to be either, right? It's exactly, we have no idea before we take the measurement which one it's going to be, and we only know that it's equally likely to be both. Right? So for fun, let's say we put it through here, and then we end up with a plus x friend that leaves the final experiment. Okay, and now you can see why this is going to get so cool is because that plus x friend, right, that I measured to have a plus, a positive component of the angular momentum in the x direction, well, if that plus x friend is confronted with a Stern-Galich experiment in the z direction, Well, remember, right? I mean, from, you learned this like 2 minutes ago, right? That the plus x state is a superposition of the plus state and the minus state. And therefore, I don't know what the z component of the angular momentum is going to be anymore, right? It could be up, it could be down. And why isn't it up, right? After all, I literally measured this particle to have a z component that was upward 2 minutes ago. But I destroyed that when I collapsed it into the plus x state. And so now when this plus x state is confronted with another Stern-Gerlach experiment, physics has to play out again, and I have to measure the z component all over again. And this is this word that your grandparents have been telling you your whole life, right? That taking measurements affects the state, right? I had that general thing and it became a spin up, right? And you say to yourself, well, maybe it's just, maybe it was always spin up. Okay, maybe it was always spin up. But then I measure it in the x direction and I try to send that through another question of spin up or spin down, and it has to make the choice again, and it very likely, half the time, will end up being spin down, right? And so the properties of that particle are really affected by the measurements that I take when I do these repeated Stern-Gerlach experiments. And this is not a mathematical trick. This, honest to goodness, happens in the lab when you line up these Stern-Gerlach experiments and try to make measurements of particles as they progress through the experiment. And it's cool, right? I mean, this is, if there was ever a reason to learn in linear algebra, it would be to understand why making a measurement of something and forcing it into a certain basis vector will then make that will change it, right? I mean, because if I put it in the basis defined by the z direction, then I don't know what the x measurement's going to be until I do the x measurement. And then when I do the x measurement, I've destroyed the measurement of the z direction. If this isn't reason enough to be a physics major, I don't know what it is. Anyway, all right, your take-home messages for today. Probability amplitudes are those decomposition coefficients, right? They tell me how much of my vector is in each direction. But they also tell me what's the likelihood of making a particular measurement when I actually go and make that measurement, right? That's a postulate, but it's one that's consistent with our observations. And those probabilities are, the modulus squared of those expansion coefficients. And I've written it here in a way where I don't know how many states there are, just to get our minds in that place where we probably soon will end up with systems that have more than two states. And that the idea of normalizing a vector is the mathematical equivalent of saying that the probabilities have to add up to 1. All right, see you soon.